now introduce the next speaker, the organizer, one of the main heads behind the seminar series, also the president of our commission, Krishina Tautwashene from Vilnius University, and she will present to us an overview of understanding the Gaia-ESO Survey detailed elemental abundances in the red giants of the peculiar galaxy cluster NGC 1851. That was the galaxy cluster Kiati already mentioned in his talk. And we're looking forward to your talk. Krishina.
So today I would like to highlight our paper of the Gaia-ESO Spectroscopic Survey on the detailed elemental abundances in red giants of the peculiar globular cluster NGC 1851. This paper is accepted for publication in Astronomy Astrophysics. So it is well known that globular clusters are quite complex systems, and very often, actually almost all clusters, they have two populations of stars. The second population may form from ejecta of mass from the previous from the first population. However, there are some globular clusters which are even more complex, like, for example, Omega Centauri. It has splitted main sequence, and this was discovered in about 1997, 2004. And those clusters are called type 2 globular clusters. So one of them is also the globular cluster 1851. And this cluster has two subgiant branches. And those two branches have slightly different metallicity that was detected by Careta in 2010, Graton in 2012. And it was raised the idea by Campbell et al. In 2012 that this could be, for example, emerging of two globular clusters. There were suggestions by Becky Young and Marino that this could be the naked nucleus of a captured and disrupted dwarf galaxy. Other people like Vanderberg, Careta et al., they propose that this could be the merger between two parent globulars which were formed in the dwarf spheroidal galaxy. It is possible to answer to those questions knowing the robust abundances of carbon, nitrogen, and oxygen abundances. And we addressed this question in our Gaia-ESO Spectroscopic Survey. With the high resolution spectrograph UVES on the VLT telescope, we investigated the spectra of 45 giants. Here they are displayed already divided to metal-rich and metal-poor subsamples. And those subsamples, it was very easy to separate using the mean abundance of S-process dominated element to iron ratio and nitrogen to iron ratio. And here on the left side, you can see already two quite well separated subgroups of 17 metal rich and 28 more metal poor subsamples, and the differences in metallicity is about 0.07 dex, like it was found in previous studies. On the right side, a similar plot of S process dominated elements to iron ratio in respect to metallicity. And here we have a slight overlap in metallicity, which is normal, having in mind determination errors, and of course there cannot be very sharp division between those two close metallicities. So we determined abundances of 29 elements, and they, in some of them in different ionization stages. And here you can see that, for example, averaged abundances in those two subpopulations of carbon are quite similar. For nitrogen, there are differences. For oxygen also, for sodium also, there are two correlations of oxygen and sodium in both populations. Also, there is difference in aluminum. However, for alpha elements, we see quite similar abundances. And for iron group elements, abundances are quite similar. And here we come to S process dominated elements, and at once we see already differences like in other type 2 clusters. And for R process dominated chemical element, europium, already there is no large difference, and abundances are a bit larger. Talking about C+N+O elements, here there are some examples how features of those elements look in stellar spectra and how we model them. For giants, C2 bands are among the best indicators while determining carbon abundance. CN bands are useful for nitrogen determinations, and luckily in this globular cluster we were able to investigate the forbidden oxygen line, which is a very good indicator of oxygen abundance. It's not sensitive to deviations from the local thermodynamical equilibrium, and very little difference is received while investigating it with 3D models. So for us, it is important to know the sum of abundances of those three chemical elements, because the deviation in the subgiant branch could be caused either by difference in the sum of C+N+O elements or in H. And here we see our result. Here is the sum of C+N+O elements, and here on the x-axis we have S process element medium values in respect to iron. And we see that in those two subsamples of stars, there is some spread of about 0.1 dex in the sum of C+N+O abundances. However, there is no difference between this sum between those two subsamples. And from the estimation of Graton et al. Of 2012, it was evaluated that, for example, if the sum of C+N+O abundances is the same, this means that metal-rich subsample is by 0.6 gigayears older than the metal deficient subsample. And if we have metal deficient subsample younger, it means that this could not be two populations of the same cluster. We should have the merge of two globular clusters. A possibility that NGC 1851 could be originated in the nucleus of a dwarf galaxy captured by the Milky Way was proposed by Marino et al. In 2014, who confirmed that the presence of a diffuse halo of stars, there are such stars co-moving with the cluster. First noticed by Olszewski in 2009, and found that it has the same chemical pattern as the S-process pure stars within the cluster. They investigated 15 such stars around this cluster. Also, Navin et al. In 2015 also found 4 probable extratidal cluster halo stars with quite large distances from the cluster, and Kuzma et al. In 2018 also confirmed a large diffuse stellar envelope surrounding this cluster. In the Revue survey, Kander et al. Also found stars associated with these clusters in the distance of about 10 degrees away from the core of the cluster. Marino et al. Noted that this cluster lies within the so-called vast polar structure of satellite galaxies of the Milky Way, discussed in Pavlovsky and Kropa 2013 and references. Do you hear me?
Yes, yes.
I do.
Yes. I
cannot change my slide. I don't know what to do.
Maybe just move your mouse. Okay. Yeah.
Thank you. So, what is the origin of this cluster? What it could be a parent galaxy of it? So, based on the Gaia space mission kinematics, Massari et al. In 2019 attributed this cluster to the Gaia-Enceladus, which merged to our Milky Way. And according to Helmi of 2018, this Gaia-Enceladus was slightly more massive than the Small Magellanic Cloud. So as we have models for the large and small Magellanic Clouds computed some time ago by Professor Pejal and me in 1995, 97 and 98. So we decided to compare abundances in this cluster with the models. And here you can see by blue line the model of the large Magellanic Cloud, by yellow dashed line the model for the small Magellanic Cloud, and the black continuous line is for the comparison of the thin disk of our galaxy. So we can see that abundances of mean abundances of alpha elements are very similar to the model of the large Magellanic Cloud. And we see that also there is a similarity in abundances of S-process elements, and another subsample has larger abundances. And when comparing abundances of R-process dominated element europium, we see that the abundance is a bit larger, and this is usual for the Gaia-Enceladus galaxy. There are studies when some stars, field stars of that galaxy were investigated, and the abundance of R-process elements was larger in comparison to our Milky Way galaxy. So according to its chemistry, NGC 1851 fits to the Gaia-Enceladus parent galaxy, and even maybe its nucleus, as suggested by Becky and Young of 2012 and Forbes of 2020. So this was our contribution in analyzing this peculiar cluster and possible scenarios of type 2 clusters. But not
time already. Yeah, you're well in your discussion time already.
Yes, I am finishing.
Okay.
So not necessarily all type 2 clusters should be merges of two clusters, of course, and there are some interesting other examples, like, for example, M22. Lee in 2020 have found 5 populations in M22 using calcium, CN, and sage photometry, and the metal poor stars were divided into 2 subpopulations, and the metal-rich stars into 3 subpopulations. So there is idea that this cluster also could be merger of 2 globular clusters, but so many populations, it is very interesting. And Omega Centauri, according to Merzos et al. Of 2021, you can see how many subpopulations are in this cluster, and here they find that the sum of C+N+O abundances are increased with increased metallicity. So this field of research is very interesting, and I believe that there will be many interesting results. So thank you.
Thank you, Christina, very much. We still have time for a few questions, and the first question is by Kiati. Please go ahead.
Hello, Grazina. Thank you so much for sharing this detailed study on the spectroscopy of 1851. I was just wondering that initially you showed that you split the population based on their metallicity into below -1 and more than -0.95. So what was the motivation for that?
So motivation was, as I showed, Oh, sorry. The motivation was this plot on the left. Abundances of S process dominated elements and abundances of nitrogen to iron ratio. You see that those stars split into two different subsamples. And when you compute the mean metallicities of those stars, we receive such values like minus 0.98 and minus 0.05.
Thank you.
Questions?
I'm sorry, I don't know how to put that hand up, so I just would like to ask a question. Grażyna, you say that you gave an examples of a few globular clusters that you think are a result of mergers of two. First of all, I think that probability of such mergers is not very high, really.
Yes,
and,
I do not say that they are.
After the merger,
I don't
after
say
the
that
mergers,
they are
I think
mergers.
that this globular cluster should be bigger, larger, sort of that. So, is there any difference in, say, radial time scale, radial scale lengths in merged globular clusters and not merged? If not, then I don't know.
So first of all, I at once started to show that I did not say that those other clusters which I provided are mergers of two. Yes, for one of them, authors say that this could be the case. But I just say that it is very important to investigate those C+N+O abundances in globular clusters to understand more about the origin and evolution. This is open question.
Okay.
Yeah, that's right.
Thank
That's
you very
right.
much.
Absolutely.
I think we have to come to a conclusion. We are already in overtime, injury time, so to speak. Thank you very much to our two speakers, Grażyna and Kiati, for nice presentations. For another, I think, quite successful example of our IAU symposium, or IAU commission meetings. Looking forward to the next one, and I hope to see many of you there again. See you next month. Thank you very much for joining.